Hello everyone, this is the talk on the optimal streaming approximation for all Boolean Max-2 CSP and Max-K set. I'm Chi-Ning, and this is a joint work with Sasha and Santhoshini, and we're all from Harvard. Okay, and the motivation and the topic of this work is about constraint satisfaction problem, CSP, in the streaming model. So CSP is a very central problem in computational complexity. And streaming model is providing a platform to study the unconditional hardness of CSP. Yeah, and one simple motivating example of this work is the Max-DICUT problem. Yeah, so in this problem, think about you have a digraph. Yeah, and the graph, I give you directed edges in the string. And now you only have very limited spaces, for example, maybe only big O log space. And I want you to tell me what's the size of the largest die-cut you can get. Yeah. So previously, the trivial algorithm for this problem only gives a 1/4 approximation. And then in a recent work by Golovnev and Velusamy, they show a non-trivial 2/5 approximation. And in the meantime, on the hardness side, there's only 1/2 approximation. We know that it requires a super logarithmic space. Yeah, so there's a gap here. And this is like the starting point of this project. Like what will be the optimal approximation ratio for Max-DICUT in the streaming model? And one of the first results of this work of ours is to show that actually the true answer is 4/9. Yeah, so we can show that there is a log space streaming algorithm that gives 4/9, maybe minus epsilon approximation to Max-DICUT, while slightly better than 4/9 require root n space. Yeah, and more generally, in this work, we characterize the approximation ratio for every Boolean to CSP, as well as K set. Okay, so to give a more concrete setup, let me start with the definitions. Yeah, so CSP. So in CSP, we'll have n variables taking value in the alphabet set sigma. So in this talk, you should think of it as the 0, 1, the Boolean alphabet. And constraint is of the form of a function f and a subset of variable s. Yeah, so for example, a constraint could be an n constraint. Yeah, a 2n constraint is like you have a 2n function and the set maybe is like 3 and 8, then this gives a constraint of x3 and x8. Yeah. So CSP instant is then a collection of constraints, and the number of constraints is denoted as n. And the goal of the CSP problem in general is to understand the optimal value of input constraint, input prob instance. And this is defined as the largest number of constraints you can simultaneously satisfy. Yeah, so here sigma is a function representing an assignment for variables to the alphabet set. Yeah, and yeah, the value will be formally defined as this. Yeah, and why CSP is interesting? Because it can encode lots of the problem we're interested in. For example, Max-cut. Yeah, for Max-cut, you have an undirected graph and you want to find the largest cut. And to translate it into CSP, you can think of a variable being associated with each vertex, deciding whether this vertex lies in the cut set T. And the constraint is like an edge. Yeah, so we know that an edge is a cut edge if and only if x or sj is 1. Okay, so the value of the corresponding CSP problem is exactly a Max-cut value. Okay, so now that we've seen the definition of CSP and so that you can at least encode the Max-cut, yeah, it turns out that actually CSP is very implicit in complexity theory and extremely well studied. Yeah, so specifically, if we want to understand the optimal value exactly, then the famous Schaeffer's dichotomy theorem tells us that it is either, the problem is either in P or it's NP hard. Yeah. So the status of exactly solve the CSP problem is very, very well understood and have a very beautiful theory. Yeah. However, it is also very natural to consider approximation setting. but now the landscape layer is not so unifying. Okay, yeah, and what is approximating CSP exactly? Now let me define this formally using a distinguishing problem. Yeah, so when we say there is an algorithm that gives alpha approximation for certain alpha within 0 and 1, it means that it can distinguish the case where the instance has optimal value greater than v, or the no instance is like less than alpha times v. Okay, so then you can know that you can see that when alpha is 1, this is the exact problem, and when alpha is 1 minus alpha for any epsilon, this is called Fourier approximation. But it turns out that not every problem can have like Fourier approximation or something like this. It is not very unifying. Yeah, and on the algorithmic side, people usually do some random sampling algorithm or SDP-based algorithm. And the hardness side, in the polynomial time region, yeah, people can sometimes give some NP hardness, but usually not tight. And one of the very interesting sub-area here is the unique game conjecture. So under the assumption that the unique game problem is hard, yeah, turns out that people can show lots of problems as a tight approximation ratio under this assumption. For example, in Max-DICUT, there's a trivial 1/2 approximation algorithm, and the SDP algorithm gives you 0.87a, and the NP hardness only gives you 0.9441, but the unique game hardness gives you exactly what you can get from the SDP algorithm. Yeah, and it is a very fascinating area and lots of open problems. Okay, but here in this work, we are interested in having a unifying theory for approximating CSP through the length of streaming model, which will provide you unconditional hardness. Yeah, so what's CSP in the streaming model? Yeah, so now because streaming model, we have much limited space. So the input now arrives in the stream. For example, you have a limited machine and a constraint arrives in the stream. And in the end, you only have like sublinear, or even you should think of it as logarithmic space. Yeah, so you cannot even store an assignment because an assignment requires n bits at least. Yeah, so the goal is only to give output the value of the optimal value of the input instance. Yeah, and since this value shouldn't be arbitrary, so we need this value to satisfy certain guarantee. For example, if we call this streaming algorithm have an alpha approximation, then we should guarantee at least there's an assignment satisfying v many constraints, and the v is great at least alpha times the optimal value. Okay, so if a streaming algorithm can give such guarantee, then we say it is an alpha approximation algorithm, streaming algorithm for the CSP problem. Okay, so now let's look at our favorite Max-DICUT problem. Yeah, so it's not hard to see that there's a trivial streaming algorithm gives 1/2 approximation. Why? Because the streaming algorithm just counts number of edges and output the number of edges divided by 2. So by conditional expectation analysis, you know there exists a cut of this size. However, interestingly, in the streaming model, people can show that this is necessary. Yeah, concretely, if you for any epsilon greater than 0 constant, yeah, to give an half plus epsilon approximation streaming algorithm for Max-DICUT requires linear space. Yeah, by the famous by the result of Capero and Krachon last year. Okay, and notice that this is quite different from the polynomial time region, because we know that in polynomial time region there exists an SDP-based algorithm, Golovnev algorithm, that gives you like 0.878 approximation. Okay, so now let us so in the before this work, yeah, like basically people mostly study only Max-DICUT in the streaming model, and for the other problem it is not that clear. Yeah, and in this work we try to give a more unifying explanation of CSP problem in the streaming model. Yeah, so the starting point is this Max-DICUT problem, and as mentioned before, there's a trivial 1/4 approximation algorithm similarly by just output number of edges divided by 4. Yeah. However, on the hardness side, there's only 1/2 approximation hardness due to the Max-DICUT. Yeah, and on the algorithmic side, the best known algorithm before our work only gives 2/5 approximation. So there's a gap, yeah, between the upper and lower bound. Yeah, and so the natural question is then, what's the right approximation ratio for Max-DICUT in the streaming model? Also, what about other CSP problems? So the result of this work is to first show that the true answer for Max-DICUT in the streaming model actually is 4/9. Yeah. And we further characterize the approximation ratio for every other Boolean 2 CSP. 2 here means the arity of the constraint is 2. So the main theorem is stated as here. It might look a little bit scary, but it's just saying that for when you give me the type of the 2 CSP, I can exactly tell you what's the approximation ratio you can achieve. And slightly beyond that, there's a lower bound, at least root n space. Yeah. And we can also generalize our result to certain CSP with larger arity. So specifically, we can show that the all result can be extended to max K set. Yeah, and the approximation ratio there is √n/2. Also different from the trivial upper bound and lower bound. Quite surprising here. Okay, so in the rest of my talk, I'll start with the algorithm side and then talk about the hardness and then give a summary and the future direction. Good. So let's start with the algorithm. So specifically, let's only focus on my Max-DICUT for now. For other problems, please go to our paper for more details. Okay, so before talking about our algorithm, maybe let's first take a look at the 2/5 approximation by the previous work of Golovnev, Velusamy, and Velusamy. Yeah, so recall that prior to their work, the only known algorithm is the trivial 1/4 approximation algorithm. Yeah, and the key idea of that work is to consider more information than the number of edges. And this information is called bias. Okay, so the bias for a vertex in a digraph is defined as the difference of in degree and out degree. For example, the following vertex, the bias is -1. Okay, and the total bias of a digraph is just the sum of the absolute value of the bias of each vertex. Okay, so why this definition is interesting? Yeah, the main motivation is that it turns out that this bias can be estimated in log-n space, meaning that this bias provides some, you can use very small space to give to get some quantity about the local information of each vertex. Okay, and the reason is just using L1 sketching from the streaming community, which is a very standard tool. Yeah, and getting this extra information of total bias, it turns out that you can utilize the relation between bias and the optimal value, and then you can give some non-trivial approximation. Okay, so specifically in GVB 17, they show that when you have certain bias, certain range of the value is not achievable. Yeah, for example, in this figure, the x-axis is the total bias and the y-axis is the range of the cut value. When the total bias is super small, then we know that the cut value cannot be too high. Okay, and they also give a lower bound showing that a certain value is achievable. Yeah, so then what's the output of streaming algorithm? It's just simply outputting the red line. Yeah, and the approximation ratio is just the maximum difference ratio among these two lines. Okay, so the key idea of our new algorithm is just improve this bias analysis by giving a more sharper lower bound by random sampling. So instead of just outputting the red line given by them using greedy algorithm, we consider some random sampling analysis with bias. Yeah, so the observation is like their analysis is not tight in the extremal region. Yeah, so we want to utilize bias to understand, to distinguish the extremal region. So we designed the following random sampling process using bias. So for each vertex, we assign to the ingoing set with probability half plus delta times the sign of the bias. And the assign to outgoing set with the other probability. Yeah, so you can observe that when delta is 0, then this is actually the trivial uniform random sampling algorithm. And when delta is 1/2, this is the greedy algorithm by assigning the vertex to the ingoing or outgoing set according to the bias. But now we are not doing deterministic, we're doing certain bias sampling. So it turns out that using this idea, we can establish new relation between total bias and cut value. And pictorially, this looks like this green line. So we sharpen the lower bound analysis. Yeah, and so that the new streaming algorithm just estimate bias and output the max of green line and red line, so that we improve the worst approximation situation and improve it to 4/9. Yeah. So the calculation here actually is not too difficult, but it's not very illuminating to explain the talk. So please go to our paper for more details. Okay, so as a summary of the algorithmic side, it turns out that we can extend this bias idea to other Boolean 2 CSP and show some non-trivial approximation algorithm. But to really show this approximation ratio is tight, we need to find the corresponding lower bound. Okay, and yeah, please go to our paper for more details on the algorithm side. But now I'll turn to the harness side to show that we can show harness that match the upper bound. Okay, so to show harness, recall that we need to show that there cannot exist a streaming algorithm using small space that gives even better approximation ratio. Yeah, and the punchline is that we need to find instances that matching random sampling bound. Okay. So how do people usually show streaming lower bounds? They usually show, we usually show from communication complexity. And so we know that from communication complexity, we usually have lots of unconditional lower bounds for certain communication gains. And the intuition and the high level ideas of how to get streaming lower bound from communication complexity is that usually when you have a streaming algorithm, if you can turn it into the protocol of certain communication problem, then once you have a lower bound for the communication gain, you have a lower bound for the complexity of streaming algorithm. Because now Alice and Bob, the player in the communication game, just sends the configuration of the streaming algorithm as their message. Okay, so in order to show the lower bound for our problem of interest, we need to find the corresponding communication gain. And we use this distributional Boolean hidden partition problem from the previous work. Yeah, so this is exactly used by the previous work of Cabral, Kennan, and Sudan, which shows root and lower bound for Max-DICUT. And the problem is like this. Yeah, this is a 2-player 1-round game where Alice has a hidden partition encoded by Boolean string X star. And Alice can send C bits to Bob, which has 2 things. One is an indicator vector W of slightly smaller length, and a matrix N encodes a matching over N vertices. Okay, and the goal is to distinguish the following 2 cases. In the yes cases, X star is we guarantee that there exists some X star such as W equals to MX star. Yeah, so this T is for things in the future. Sorry for typo. Yeah, and the node distribution is where this W is not correlated to N and X. It's just a uniform random string. Yeah. So the Similar result by Golovnev et al. They show that this problem requires root and communication. And once we do some bootstrapping by having some parallel repetition, we can boost the number of copies of Bob, and this will be useful in increasing the number of edges in the future. Okay, so yeah, so this is an example of the problem, and maybe you can pause the video to see if you can see this is a yes or no case. And turns out that it is a yes case because this X star is a hidden partition. But now the important thing is to see why this problem connects to Max CSP. For specifically for Max-DICUT, yeah, the connection is that the intuition is to use this indicator as a W to pick the edges. Yeah, so for Bob 1, you can see I will pick the first edge, which is 2, 3, and insert to the streaming algorithm. And then Bob 2 will pick the first and the third edges. And for Bob 3, yeah, so streaming algorithm is treated as a message string sending throughout. And we'll use the value of the streaming algorithm to decide whether this is a yes case or no case. It turns out that we can show that yes case corresponding to having a perfect cut, and no case corresponding to there's basically no non-trivial cut. Yeah, so now we can have a more unifying view of using DBHP to provide a reduction by thinking of W picks the edges, select the edges for us. So the yes distribution just selected the cut edge, and the no distribution only select random edge. And it is also helpful to consider yes prime distribution, which only select the edge lies in the same side. Okay, so with this graphical view in mind, we can have a unifying understanding of Max-DICUT by, yeah, we just insert the edge into streaming algorithm, and the output value will match the cut value, so that we can use the streaming algorithm to derive the protocol. Okay, and how about for Max-DICUT? So then this becomes very straightforward. Yeah, Alice will use the cut she has to create some bias edges inserted into the streaming algorithm. And the Bobs just inserted a directed cut on both directions to the streaming algorithm. And we can show that the yes distribution will corresponding to some digraph with large cut value, and no instance will corresponding to digraph with small cut value. And it turns out that we can design this bias setting properly so that the ratio of these two values will exactly match the value we can achieve in the algorithmic side. Okay. And similarly, we can do the same things for other two CSP problems. Yeah, but due to a time limit, I won't explain here. You can go to our paper for more details. Okay, so as a summary, yeah, the techniques provide us a very unifying and graphical way to understand the hardness of approximating Boolean 2 CSP in the streaming model. Okay, so to conclude, yeah, we provide type analysis for approximating Boolean 2 CSP in the streaming model, and also can do the same thing for max case set. And in a high level, this is demonstrating that in streaming model, the local random sampling actually is optimal. Yeah, we can have a unifying understanding of approximation here, not like in the polynomial time regime. And for future directions, yeah, in short term, it is very interesting to improve our root n space lower bound to a better lower bound, because that we know that in Max-DICUT, there's linear lower bound. And in the midterm, yeah, it's also interesting to generalize to more family of Boolean CSP problem. Yeah, like with larger arity or with larger alphabet set. And in the long run, it's also interesting to study like how to demonstrate how to explain why local random sampling is optimal in the streaming setting. Like, is there can we have a very unifying and beautiful theory for the streaming model in terms of approximating CSP? Okay, so yeah, so this is the end of my talk. Yeah. Yeah, please go to our poster session or our paper for more details. Thank you for your attention.